So talk me about pressure. I am the only one to present this afternoon. My name is Benoît Stoll. I'm from the French University, French Polynésie University. The title of my presentation is Geomatic in Tetiaroa toward an atoll under environmental monitoring. I subtitled it Tetiaroa GIS database because of the thematic of the session, which is about the tools. So I will focus on the tools I develop in Tetiaroa. The co-authors are Hervé Bossin from Institut Louis Mallardet, Cécile Gaspard and Martin van der Helm from the Temanao Association, Armin Groen, Tauguo and Serkan Mural are from the UTH Zurich. My students, Mehania, Xenia Jost and Manari Longine. And finally, Jean-Yves Meyer from la délégation à la recherche et Frank Murphy from Tetiaroa Society. So Tetiaroa is located at 50 kilometers from Tahiti, north of Tahiti. It's an atoll, a closed atoll with 12 motus. It was 13, but one motu disappeared years ago, and the surface is 34 square kilometers. So a little history about Tetiaroa. Tetiaroa was the Tahitian royalty favored retreat with a lot of traditional uses and ceremonies. In 1904, the Tetiaroa was given to Johnston Walter Williams, who was a dentist from the royalty family, and it became a private atoll, and there is a development of a copra plantation. You can see the image here. It's an aerial photo from 1955 with the copra plantation. In 1967, Marlon Brando bought the atoll, and the coconut grove came fallow. And the last, in 2014, the Brando Resort opened on Etaimotu. So it was the beginning of an environmental conservation. So the Tetiaroa Society promotes education, conservation and research on Tetiaroa, and there is a lot of researchers from around the world who came to Tetiaroa to study some scientific purpose, and there is a strong need to share some background data, a strong need to store the searchers and the associations data in a common system, and a strong need to compute data in relation with each other and to monitor environment parameters. So a geographic information system is a useful tool to make of Tetiaroa a global observation and conservation project. I will present you the various projects I'm involved in, which contribute to the global mapping effort on Tetiaroa, and to start building the geographical database in relation with my partners, IDEA program, and Institut Louis Mallardet, Temanao, Tetiaroa Society, etc. So for a good GIS system, we need to have some image data. So the historical image database starts in 1955 with this aerial photography. Then in 1981, another aerial photography, 2001 and 2004, still aerial photography in color. And in 2010, the first satellite images from Tetiaroa, Worldview 2, same image as in 2012. And the last image is from 2014 with a Pleiad image. I'm sorry about the colors, it's not very... Anyway, there is a last set of data who was acquired last year. It's a LiDAR data. So LiDAR, it's mainly a 3D point cloud of Tetiaroa with 1.42 billion points with an average point spacing of 16 to 20 centimeters and a vertical accuracy of 4 centimeters. You can have access to some very good information on the vegetation on this kind of images I'm sorry, the image is quite bad, but you can see the canopy of the coconuts, but you can see also the understory of the coconuts. It's very interesting. And from this kind of data, we can extract two products, the DSM, Digital Surface Model, and the DTM, Digital Terrain Model, mainly the canopy and the ground. The first project I am involved in Tetiaroa is the geomorphological mapping. So we start to process all the data, all the image from 1955 to 2014 with a very simple class set mapping the sand, the aragonite, the vegetation, the swamp vegetation, and the swamps. And we did that for each date. So here is the result in 1955, 1981, 2002, 2004, 2010, and 2012. 2014. Okay. From this result, we conducted a diachronic analysis, mainly to check if the motus are moving or not. So there is two types of motu in Tetiaroa, the rocky motus, the bedrock motus. They don't have no significant change, except for a few sandbank here, you will see. So you can see 1981, 2001, etc. So mainly the rocky motus are not moving, no problem. On the other side, there is the sand motus, the sandy-based motus, who can move a lot depending on the meteorological events like cyclone or swell. And for example, here, Taunarai in 1955, we don't have the information in 81, but in 2001, the motu has lost almost 2/3 of its surface and moved from 265 meters, which is huge. Since 2001, the motu didn't move significantly. So during this study, we noticed that there is some beach erosion in Tetiaroa, and it is a problem because beaches are the nesting area for a lot of species like turtles or birds. The problem with the erosion with the scarps you can see on the pictures is that you can't detect them on the aerial photographies or the satellite images. So we have to find a way to map these scarps. So I'm sorry, it's very bad. The image is very bad. We processed the slopes from the DTM. The DTM is a 3D modeling of the motus, and we process the slope. And maybe you can see here in white. That's the vertical part of the image. So from this, we can extract very easily the scarps. And we produce the global map of scarps in Tetiaroa. So each red line is a place where the beach is has a problem of erosion. Okay. The idea is to monitor these scarps areas and to see how they will evolve. And we will not in the future use some LiDAR data because it's too expensive. So I think we will use some drone mapping, 3D mapping, to do the same kind of work for cost manner. Another project who helped to build the geographical database is a mosquito project conducted by ILM, Institut Louis Mallardet. They eliminated mosquito species on this motu, on Etaï. Mainly because there is the hotel and the clients and they don't want to be bothered by the mosquitoes. And for this, the scientific in l'Institut Louis Mallardet, they took some data, the capture data and the release data of mosquitoes. They put some traps around the motu and capture all, and every day they check if they found some mosquitoes or not. So this database is from 2014, so it's almost 4 years now. It's very important. On the other side, there is the Morea IDEA project, which aims to modelize this kind of thing. And they want to do a modelization of this experiment in order to understand the factors which contribute to the elimination of the mosquitoes, in order to test some scenario, in order to improve the method eventually. So there is strong need to build a geographic database. That's where I am working. And so I had to map everything correlated to the mosquitoes, such as the trap localization, the release sites, and some environmental data. So the cartography of Onetahi started with this image, which is a Pléiade 2014. And the first thing we did is a map of the vegetation with a very simple and unorthodox mosquito class set. It's a kind of vegetation which are important for the mosquitoes. We mapped all the rodent tracks. You can see that here there is the tracks from the hotel everywhere with a DGPS. We mapped all the buildings, containers, technicals. So it's very big job to map all these buildings here. And then we mapped all the place, the localization of the mosquito trap for the modelization. So this project is mainly very important for this motu on Onetahi because we put a big effort of mapping on this motu. So it's very important. Another project we conducted was about the turtle. Temana Temana, which is an association, is looking for the turtle nest in Tetiaroa, marine turtle nest, and they are collecting data since 2007. So we have 11 seasons of data collection on the nest localization in Tetiaroa, and about 3,800 nests discovered. So our work is to put all this data in the GIS system. So you can see here, each point is a nest, a turtle nest, for all the years here. From this, you can process some kind of analysis. For example, we process an analysis about the comparison of reef distance between the nest and the reef and the local density of nest. As you can see on this map, the green points are the highest densities localization. So everywhere here there is a lot of turtle nest. So the idea was to check if we can see on this map that these places are quite close to the reef. The reef is a blue line. So we wanted to check there is a correlation between the distance from the nest to the reef and the density. So for each nest, we processed the distance to the reef and the local density of nest. And this way you can make some kind of analysis. So the general trend here is that the farther the reef, the smaller the nest density. And we have here a special points because the mean distance between nests in this high density area is way closer than expected. So we can maybe think that the beach's proximity to the reef is an important factor for the turtle. Of course, it's not that simple. For example, you can see here that there is quite few turtle nests, and we are very close to the reef. So maybe here the explanation is the beach morphology or the obstacle. Maybe the turtle finds some rock and can't climb the rock, and it's not a good place for them. And here, this motu, there is a very high density of nest, but we are quite far from the reef. So it's not that simple anyway. So throughout those experiments, those studies, we have the need to improve the GPS localization in Tetiaroa. So in 2018, last year, Temoana has been given an RTK base station, an RTK receiver, and a radio repeater station in order to have a centrimetric differential GPS localization, which is quite expensive material. But now we have this material. Every scientist going to Tetiaroa can use this, and it's very, very good for the mapping. So we can use this kind of precision tool for the mapping. For example, the coastline vectorization. I will show you an example. And for the turtle nest parameters retrieval, such as altitude, slope, high tide, red line, etc. I will show you. So the coastline monitoring, it's important to monitor the coastline in every MO2. So we use the GPS every year to take the coastline. Eventually, if there is a meteorological event, we can go and do the same job. The red line monitoring, red line for the turtle, it's the highest tide boundary, you know, because the turtle nest, you don't have, it's dangerous for the turtle nest to have the water coming on the turtle nest. So there is always a decision from the volunteers when they find a nest. They need to see if the nest will be submerged by the sea, and if it's the case, they need to move the nest as quickly as possible. So there is a decision to make. The red line program is to have an up-to-date red line, which is the highest tide boundary. And with a precise nest localization, we will be able to take a decision very quickly and safely. So that's what we did on this MO2. So what we need for this program, the red line monitoring, we need a simple DGPS material for the volunteers. So when they find a nest, they can just check if they are on one side or on the other side of the red line. And of course, we need to update the red line very regularly, every year or after each meteorological event. So we can do this for the red line by monitoring just walking on the beach, like this, with the GPS, or to process it if we have the 3D model, for example, for a drone or for LiDAR, and the tide gauge to modelize the red line. Something completely different. This year we started to map the archaeological sites in Tetiaroa to include them in the database. It's not very environment related, but it's quite important. So we started the work with the Williams plantation on Rimatu Motu, and we will extend it to all the atoll this year. Maybe we can get use of the LiDAR data because the LiDAR DTM anomaly could indicate some archaeological sites hard to detect under the canopy. For example, you can see on this image this kind of structure here. We don't know yet what it is, but maybe could be some archaeological sites. We have another example here. Voilà. All the data are, there is a peer review available online on my web page. So you can go and check which vector layers are available. For example, this is the MO2 on Itaï. So, in conclusion, the future, so Tetiaroa is a very simple case. It's a bounded territory representative of a typical atoll, Polynesian atoll, with major environmental issues to monitor. And there is numerous scientific activities in Tetiaroa. So the GIS is already substantial, but we are going on the mapping effort. So we have some project for this year, next year, to complete the archaeological sites integration, to complete the vegetation map with the use of LiDAR and worldview 3 images, to finance a small high-precision DGPS for the volunteers from Te Manau Te Moana or the scientists, to get regular data acquisition every year, every 2 years, drone, satellite images, and to include as many other thematics as possible in this database. So, thank you. I would like to thank my students, Xenia, Manari, and Mehani, who spent a lot of time in Tetiaroa, hard for them. And thank you very much.
Okay, thank you, Benoît, for this colorful presentation. So, wish.